Hey everybody, welcome. We are continuing our basic factoring series with quadratic special cases. These come up in most algebra classes, but sometimes we're just given a couple formulas that we're told to memorize. In this video we're going to explain why these formulas work and go through multiple problems step by step. Before we get going, go ahead and like and subscribe to make sure you don't miss out on more math tutorials in the future. Before watching this video, it's helpful to know the distributive property as well as some perfect square integers off the top of your head. You should be familiar with quadratic expressions and some common factor-based factoring techniques. Everything you need is covered in the first few videos in this playlist, so feel free to check those out first, then come back to this one if you need a refresher. This video will show you how to identify differences of squares and perfect squares, derive the formulas for both of these special cases, factor differences of squares as products of conjugates, we'll cover what that means, factor perfect squares as squared binomials, and once again, this video is going to stick to integer coefficients only so we can focus on the algebra of factoring, but decimals and fractions are coming up in future videos. Alright, let's do some math. First up, differences of squares. In case you're not familiar, a theorem is any statement that's proven to be true. This theorem says that for any numbers u and v, u squared minus v squared equals quantity u plus v times quantity u minus v. We can call u minus v the conjugate of u plus v and vice versa. And in general, anytime we have the same two terms joined by opposite signs, plus and minus, we can call them conjugates. Let's show why this formula in the theorem is true. We'll start by expanding the product of conjugates here. There are lots of ways to think about the expansion, but one of the simplest and most clear is to use the distributive property multiple times. Here, we distribute the quantity u minus v to the u and the v from the other factor. Notice this sets up two more distributions for the next line. Now we have four relatively simple terms and just need to do some cleanup. Keep in mind, uv is the same as vu, so they cancel, and this gives us u squared minus v squared. Great, we did it! This formula has to be true because all of these expressions are equal. And note, the name difference of squares is a literal description of this expanded form. We're subtracting two different terms that are squared, u squared and v squared. Okay, here's a quadratic, x squared minus 64. Since x squared and 64 are both perfect squares, this is a difference of squares. Let's identify u and v that gives us these two squares. If we set u equals x and v equals 8, then u squared is x squared, and v squared is 64, so they check out. Based on the formula, we can use this u and v to write the factors in one step. We just need to form the conjugates. In our case, the conjugate factors are x plus 8 and x minus 8, and here's our factorization. X squared minus 64 equals quantity x plus 8 times quantity x minus 8. And that's it. That's how we factor a difference of squares. Now, you'll notice I didn't mention taking a square root to find u and v from u squared and v squared, and there is a reason. We'll cover it in a future video, but for now, here's a question. Why isn't the square root of x squared equal to x true for all values of x? If you have an idea or know the answer, go ahead and drop it in the comments. If you're curious, but not quite sure why this is the case, like and subscribe so you don't miss the answer. Next up, we have a couple exercises. If you have a handle on the technique, consider skipping forward to try them independently. I'm going to cover the solutions in full detail. So let's go. Here we have 81x squared minus 1. So we want u squared and v squared to line up with 81x squared and 1, respectively. Let's take a look at the 81x squared. 81 is 9 squared, so we can sub that out. Now, the 9 and x are both squared, so we can pull the exponent outside. We can see that we're squaring the quantity 9x. For the other term, 1 is equal to 1 squared. These two facts give us u equals 9x and v equals 1. Just to verify that these are solid choices for u and v and to get it recorded on our paper, this gives us u squared equals 81x squared and v squared equals 1. Now that we have u and v, we factorize as the product of conjugates, u plus v and u minus v, so that 81x squared minus 1 is quantity 9x plus 1 times quantity 9x minus 1. Great job! Let's try one more of these, this time with two variables. 4x squared minus 121y squared. We need u and v. let's look at the 4x squared. 4 is 2 squared. Pull out the exponent. So this tells us we want u equals 2x. What about v? 121 is 11 squared. Pull out the exponent. This tells us that we should set v equal to 11y. There's our u and v. Let's just check while we're at it. These choices give us u squared is 4x squared and v squared is 121y squared. Now we'll construct the conjugates u plus v and u minus v. We get 4x squared minus 121y squared equals quantity 2x plus 11y, quantity 2x minus 11y. Great work, everyone. If you have any questions about these differences of squares, go ahead and drop them in the comments. For now, let's move on to our next special case. Perfect squares, or more precisely, perfect square quadratics. Theorem. For any numbers u and v, u squared plus 2uv plus v squared equals quantity u plus v squared. Let's show that this is true, and again, the most straightforward approach is to start with the factored form and expand. Quantity u plus v squared is u plus v times itself. We can distribute one copy of u plus v across the other. Then we distribute in both terms so that we get u squared plus uv plus vu plus v squared. uv and vu are equal, so we can combine them as like terms, and we get u squared plus 2uv plus v squared. And that's the proof. This also shows us why we call it a perfect square. I didn't mention this term in the last section, but we can refer to u plus or minus v as a binomial. U squared plus 2uv plus v squared factors as the square of a binomial, so in that sense, it's a perfect square. Let's look at x squared plus 14x plus 49. We want to verify that this is a perfect square. And just like last time, in the process, we'll get all the pieces that we need for the factorization. We're checking against this form, u squared plus 2uv plus v squared, and we need u and v to align with u squared equals x squared and v squared equals 49. In this example, it doesn't have a huge impact, but we can also take a convention that the sign of the linear term, the middle term, will go with v. So let's take u equals x and v equals positive 7. Square both of them to verify that we get u squared equals x squared and v squared equals 49. Finally, we check against the middle term. Okay, so 2uv is 2 times x times 7, which is positive 14x. Great! Since all three terms lined up, we can conclude that the quadratic is a perfect square. Once we have u and v, like with the difference of squares, we can factor in one step. We just need to recall the squared binomial from our formula. So here's our formula again. We take u plus v and square it. So x squared plus 14x plus 49 is quantity x plus 7 squared. And that's the idea. We have a couple more exercises coming up, so feel free to try them independently if you have the hang of it. It's also okay to make mistakes. This is actually a great time to make mistakes because the stakes are very low. There's no bad grade, no one's going to chastise you, and I'll support you 100% in getting back on track. Consider trying it out, but either way, here we go. 25x squared minus 60x plus 36. If you think this looks scary, that's okay. Our method is going to handle it, no problem. So, what do we need to do first? We need u and v so that their squares line up with the quadratic term and the constant term. To get u, let's look at 25x squared. That's 5 squared x squared, which is quantity 5x squared. So we'll choose u equals 5x. 6 squared is 36, but we also want to align the sign of v with the sign of the middle term. So we'll take v equals negative 6. Squaring both of these as a sanity check, we get back 25x squared and 36. Good so far. Next, we check against the middle term. 2uv is 2 times 5x times negative 6. Multiplying that out, we get negative 60x. That lines up with our middle term, and so we have a perfect square. Not only that, but the factorization is just the square of u plus v. So we get 25x squared minus 60x plus 36 equals quantity 5x minus 6 squared. Next exercise has two variables. Let's take a look. Here we're factoring 16x squared plus 24xy plus 9y squared. We need to choose u and v. We can write 16x squared as the square of 4x. We can write 9y squared as the square of 3y. So we can choose u equals 4x and giving v the same sign as the middle term, v equals plus 3y. As a sanity check, we square both to see that u squared becomes 16x squared and v squared is 9y squared as desired. To verify that it's a perfect square, we check 2uv against the middle term. We get 2 times 4x times 3y, which is plus 24xy. Everything lines up, so this is a perfect square. The original quadratic then factorizes as quantity 4x plus 3y squared. Great work, everyone. We did it. If you have any questions about these perfect squares or about the differences of squares, go ahead and drop them in the comments. Let's briefly recap what we covered. First, a difference of squares is literally a difference of squares. That is, it's an expression where we subtract two squared terms. Differences of squares factor as products of conjugates, which we proved in the other direction by expanding that product. A perfect square quadratic has this particular form, u squared plus 2uv plus v squared, and factors as a squared binomial, specifically the square of u plus v, and we showed in our examples that this one formula is enough to cover cases where v is positive or negative. We don't necessarily need a second formula for the case when v is negative. So that's how we handle these special cases of quadratics that appear frequently in algebra and beyond. And you want to practice until you can spot them right away in the wild and factor them efficiently. It's not a bad idea to practice the expansion direction either, the direction that we used to derive the formulas, to prove the formulas in the first place. Thanks for watching, everyone. Don't forget to like and subscribe so you don't miss the next tutorial. Let us know in the comments if you have any other questions or specific topic requests. Drive under the speed limit, not under the influence. Take care of yourselves. Take care of each other. I'll see you next time.